experimental probability is similar to theoretical probability, except that you're basing your probability off of what you actually see from an experiment. So in theory, when you roll a die, every number on the cube is equally likely, right? And getting the probability of getting a 1 out of 10 rolls would be the same as the probability of getting a 5 out of 10 rolls on that die, because all their theoretical probabilities are 1/6. However, when you actually run your experiment, when you actually toss a die 10 times, does it happen that the theoretical probability is what you actually see when you throw that die? Not always. Maybe depending on the force you use, depending on the roll. So the experimental probability might be a little bit different from your theoretical. You will need a graphing calculator for the end of this lesson. So if your classroom has one, go grab one. If you don't have one, you can just do the example with me. But it's kind of fun to be able to do it yourself. Go ahead and pause and copy down your target for today and read this little picture that I have, and then press play when you're ready to get started. So we are going to be determining the experimental probability of an event and using it to make predictions, and that's what this picture is about. So a business might look at their products that they're producing, figure out how many have defects or how many come out correctly in their assembly line out of a mass of 1,000, and then they might use that to make predictions for if they were making 1 million or 10 million of those items. Whenever a company figures out the cost of their product, they have to take this into consideration, because if there's a couple cars in this picture that are going to come out not right, then the ones that they do sell, the ones that are right, need to absorb the costs for these ones that were kind of a waste. So predictions will be helpful from an experimental probability. You have a bunch of definitions at the top of your notes page. So an experiment is an activity involving chance. Whenever you do one of your trials, it's one of the repetitions in your experiment. So if your experiment is rolling a die, then when you throw that die once, that is one trial. When you throw it the second time, that is one trial. The outcome then is each possible result. We see what comes out in that. So on a die, it'd be 1, 2, 3, 4, 5, or 6. The sample space is going to be the set of all possible outcomes. So that's what we're looking at in our first two examples. In example 1 and example 2, I want you to identify the sample space and the outcome shown for each experiment. So the sample space is always a set. I'm going to label mine SS for sample space, but however you write it, it must be in these curly brackets, okay? You don't necessarily need this, but I like to label it. You definitely need them in the brackets because it is a set. Last time we saw sets with domain and range, we used those curly brackets. So in this picture, in spinning a spinner with 4 different colors, where R is red, P is purple, G is green, and Y is yellow, what is the sample space, or what is the set of all possible outcomes? Well, you can spin and get red, you can spin and get green, or yellow, or purple, right? Now I am going to just use the first letters here because we have a key right here. If you didn't have a key, you would want to write out those words. What is the outcome then that is shown in the picture, or when you did this trial of what you're looking at is what you got? Your outcome was green because that's what you landed on. And I might write the whole word here just to make sure we know. But if you have a key, you can just write the G. For number 2 in your experiment, you're going to be rolling a number cube and also tossing a coin. So what is your sample space when you're doing both of these? Well, on the die, we know that we can get 1, 2, 3, 4, 5, or 6. But we're also going to flip a coin with that. So we can get 1 with the heads, 2 with the heads, 3 with the heads, 4 with the heads, 5 with the heads, or 6 with the heads. But those aren't the only outcomes. What am I forgetting? Well, I could also get 1, 2, 3, 4, 5, and 6 with the tails. Oops, sorry. So you need to write them all down. 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, and 6 tails. These should be in a set, so they must have curly brackets. You can separate them with commas. And the order of which they appear does not really matter. I would follow some sort of method, though. So I went with all the heads first and then all the tails. What is the outcome that is shown then? If this was what I had when I ran one trial in my experiment, I landed on a 4 heads. So So that's just some vocabulary that goes along with probability. We talked about event and probability yesterday. The experimental probability is going to be the number of times the event actually occurs out of the number of trials that you run. So fill that in. Theoretical probability was the number of times you can get your event out of the total possibilities, right? This is very similar, but it's the number of times it actually does happen, and it's out of the total number of trials. On the bottom of that front page, you have a blank number line. I want you to fill in these words above each of these points. So at the very left end, you're going to write impossible. At the very right end, you're going to write certain. Draw a line right down the middle if you don't have one on there. And right down the middle, it's as likely as not. We're just kind of describing the probability. So when you think about probability, probability is out of 1 or 100%. So if something is certain to happen, what is its probability? It's absolutely certain to happen. It'd be a probability of 100%, right? If there's any chance that it could not happen, it would not be certain. So certain would be like reaching into a Skittles bag and pulling out one piece of candy. What's the probability of getting any color? Well, then that would be certain because all the colors would work. The other end of that, then, is what's a probability that's impossible? Well, if it's truly impossible, the probability would be 0. And right down the middle, as likely as not, would be 50%. So the probability of getting an even is as likely as the probability of not getting an even. So that would be 50% on a die. In between 0 and 50%, you're going to have, you could describe it really as unlikely. You know, if you were here at 10%, that's very unlikely. And if you were here at 40%, that's still unlikely, but it's close to as likely as not. And then anywhere between 50% and 100% would be likely. So again, if you're over here at like 95%, it's very likely. If you're over here, you know, it's a little bit better than as likely as not, but it's not very, very likely. So we're going to use these words on the next example to just describe each event. So when you're done, go ahead and turn the page. Write impossible, unlikely, as likely as not, likely, or certain to describe each event. You don't have to actually find the theoretical probability here, but it may help to think about it. So a shoe is selected from a pair of shoes and it fits the right foot. If this was your event, what would be the probability? How would you describe it? Well, since a shoe is selected from a pair, how many is in a pair? Just 2. What's the probability? How many of those from a pair are going to fit the right foot? Just 1. So this would be as likely as not. Again, the words are our answer because that's what it's asking for. Oops. But you can think about the probability to help you figure it out. All right, the next one. Ryan correctly guesses the last digit of my phone number. What do you think the chances are of that? How likely is that going to be that he correctly guesses the last digit? You're probably already saying this is pretty unlikely. Let's think about the actual theoretical probability as well. How many digits are there that could be my last digit of my phone number? I hope you didn't say 9. Hopefully you're saying 10 because you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And only one of those can be the last digit of my phone number, so 10%, pretty unlikely. Masha pulls a green marble from a bag of all green marbles. Well, that's definitely certain. No matter what the bottom is for the total, the top is going to match it. So this would be like 5 over 5 or x over x. It's definitely going to happen. And then the last one, a randomly selected month contains the letter R. So when you're thinking about the months, you probably think about this already. How likely is that going to be? Probably pretty likely. Let's think about the theoretical probability. So these over here are theoretical probabilities. Well, we would have January, February, March, April, no May, no June, no July, no August, September, October, November, December. So 8 out of the 12 months. 8 out of 12, that reduces 2/3. That is definitely likely. It's 66.6%. So conducting an experiment, you can find the experimental probability. You're just going to use the results that actually happened and not what would happen in theory, okay? For this experiment, they spun a spinner, and we're going to use the table to compute the experimental probability. Remember, with experimental probability, the denominator is always the number of trials, so always add it up first and figure out how many trials you ran. This adds up to 40, hopefully you got that. So if we want to find the experimental probability of landing on orange, and notice I am writing my probability notation. How many times did I get orange? 10 times. Out of how many times did I run, how many trials did I run? 40. Always reduce your fraction, and you can also write your percent. Definitely make sure you always reduce your fraction. What's the experimental probability? That it does not land on green. So how many times did it not land on green? So how many trials did we run? Well, not green would be these three. 15 and 10 is 25. Reduce your fraction. And then you can also find your percent. You can use your calculator here if you don't know this percent, so go ahead and take a second to do that. 5 divided by 8, remember that'll give you the decimal form, and then you want to write it as a percent. So 5 divided by 8, hopefully you have it by now, is 62.5%. And then the nice thing with the experimental probability is we can use that to kind of predict the future. We know it's not, foolproof, it won't always be exact, but it'll give us an idea or an estimate of what would happen in the future. So a manufacturer inspects 500 strollers and finds 498 of them to have no defects. What is the experimental probability that a stroller chosen at random has no defects? So the experimental probability of no defects would be what fraction? Well, we want the no defects, and that's 498 no defects over the total, which is 500. You can reduce this because they're both even, so divided by 2, that gives you and then you can use your calculator to get your percent. You're just going to divide, get that decimal, and that gives you 99.6%. Then to make your prediction, you have two options. So on the B, the manufacturer shipped 3,500 strollers to a distributor. Predict the number of strollers likely to have no defects. You can either set up a proportion or you can write an equation. If you do a proportion, we know 498 out of the 500 have no defects. We want to know how many out of 3,500, so that's your total, would have no defects. There's your proportion. Or what you can do is write your equation, taking this ratio right here, which is a decimal. You just have to make sure you put the decimal in the equation. So it would be 0.996, and just multiply that by the total, which is 3,500. Both of these would be good work. I would write them both down now on your notes just so you remember you have those options, but your teachers will accept both of those. Go ahead and use your calculator to do your proportion or your equation, and your answer is 3,486 strollers with no defects. Make sure you put a label on there because we do want to know what we were solving for. Perfect. All right, so the last part of this is just a little bit of fun. So I'm going to show you how you can use your graphing calculator, but I'm running out of time on this video, so it'll be on a separate video. If you want to run an experiment without using dice but just want to use your graphing calculator, this will show you how. So you can go ahead and you can end this video, and the next one will help you finish the last example. You do want your own graphing calculator to do this, but if you don't have one, you can just follow along with mine.